We're gonna proceed. Linear search is a technique where we visit each and every index one by one in a unidirectional way. Yes, you are right. So this is the kind of technique we follow in linear search. So what is the most obvious way that comes to mind when you are searching in an array? Because see in this problem, in this array, you can clearly see that we are trying to find element 8. Okay, but it is this thing is visible to you, but in the array form, when you are writing a program, you don't know what are the elements present in an array inside an array. Maybe it was entered by the user. As a uh, programmer, you don't know what elements are stored in the array. So how can you find whether a particular element is present in the array or not? What is the most obvious idea that comes to mind? Any answers, any guesses? You can turn on the mic and speak. Okay, so no answers. The most obvious thing we can do here is by going one by one and checking each index whether our element is present there or not. Like it's like knocking the door of each room and asking whether our target element is present here or not. In this case, our target element is 8. Target is 8. And we have to search in which index 8 is present and whether even the 8 is present or not. So at first, we're gonna encounter this index and let's check whether 8 is present here or not. So we are currently at this index and let's see. We are checking 8 is present here or not, and the answer comes as false. 1 is not is equal to 8, so we obviously go to the next one. Now this is the second index, and we again check whether 8 is present here or not. So this is the most easy way of searching. Am I right? We go one by one and check whether our target element is present here or not. So we keep on going, keep on going, keep on going until we find our target element 8, which is at index 7. So this is the main idea behind linear search. This is the main idea behind linear search. So is the idea clear? Give thumbs up if you understood the idea, or you can ask any doubts. Okay. So no doubts. Okay. So we're gonna proceed further. So what we can write about the program. So let's write the for loop here. Just a second. Okay, so how would the for loop look like? Like we are traversing the whole array, and it would obviously start from the 0th index, and it would end at the last index, which is at this case is 8. and it would travel. We would traverse the whole array, and we would just check whether the ARR of I is equal to our target or not. If we find that it is equal to our target, then we have found the element. The search is successful. And if we traverse the whole array and still we haven't found that element, then our search is unsuccessful and the element is not present in our array. This is the simple logic behind linear search. So, is there any doubt about this? Give a thumbs up if you understood the logic. Okay. Okay. So, can we code it right now? Let's code it right now. Okay. So, I'm gonna go to VS Code and let's code it up. At first, we're gonna we are not gonna assume the array. Okay, we're gonna take the array from the user because that is the most real world scenario you're gonna encounter. You're not gonna give it array by yourself. The user is gonna enter the array. So we're gonna take the array from the user. Let's say the max size is of 100, and we're gonna ask the user enter the size, and we're gonna store it in n. Let's declare the n variable. So we have extracted the size. Now let's ask the user about the inputs. Enter the array elements. So we're gonna run a loop starting from 0 to n, and we're just gonna uh, put this inside the array. So now the final input we're going to take from the user is what to search. Like enter the element to be searched. And we're going to store it in target. Let's declare the variable target. So here it is. So our input part is ready. And now we're going to start our linear search. Okay, so for int I is equal to 0, I less than n, I plus plus. So we're gonna running the loop from 0 to n, n minus 1. That is I is less than n. So it would run up to n minus 1. That is the last index. So we're gonna check if target is equal to ARR of I. Then our answer is that I, let's just take an answer index variable. And this answer will be storing the index of the element when trying to search. So this, and now we're gonna print. Let's first check whether we found the answer or not. If answer is equal to -1, cout Okay, so I hope this is okay. Not index answer. Okay, let's run the array once and check whether everything is working correctly or not. Okay, so I'm expanding the term. Wait. Is it visible? Like, can you see at this part? This is the output. Okay, let's first clear it. Okay, so first the user is up. The program is asking for us to enter the size of the array. Then enter the array elements. So we're gonna just enter 1, 2, 3, 4, 5, 6, and now the program is asking us to enter the element to be searched. So let's enter 5 and let's see. Okay, element, the output is element found at index 4. Element found at index 4. That is, if you see the array 1, 2, 3, 4, 5, at 0th index 1 is present. So obviously at 4th index 5 would be present. So our program is running correctly. And let's check whether if I enter something that is not in the array, whether it would be running or not. Now, obviously, 6 is not present in our array. So let's enter 6 and let's see what's the output. So element not found. 6 is obviously not in our array, and thus the program is telling us that element not found. So we're gonna dry run the program once. If that's gonna make things more clear. Okay, so everyone, did you understand the program? Do we need to dry run it? Any suggestions? Okay, so we're proceeding further. The first, the answer variable was initialized with 1. As the for loop was going from I 0 to n minus 1, it would traverse the entire array one by one. The 0, 1, 2, 3, 4th, 5th, 6th index, like this. When any of the, at any point of time, the ARR of I becomes equal to target, then the answer index gets updated to the current value of I, at which index the target is present. If the whole traversal is complete and still ANS is equal to minus 1, then we can say that there was no occurrence where target was present. So that's why here I have checked whether answer is equal to minus 1 or not. If it was equal to minus 1, then cout was given as element not found. because the whole traversal was complete and answer is still -1. So we can tell that element was not found. Element was not present in the array. So is this clear? Give a thumbs up uh, if anything was not clear. You can ask. Okay. So we are proceeding further. This this is a definition of linear search. You can just go through it. Linear search algorithm is also known as sequential search algorithm. It's a simple searching algorithm that traverses a list or array sequentially. So how does linear search algorithm work? This is a written definition here. You can go through it. And if any problem, you can raise the doubt. So what about the time complexity? So are you guys aware of the time complexity? Like, do you have any idea of time complexity, what it is? Tell me in the chat box. Okay, not complete idea, but something to do with operations on n, as far as I know. Okay, so time complexity, more or less, I'll giving you a rough idea. Like, it's not the detailed idea, but it's the overall idea, a rough idea, to be honest. So time complexity is a tool by which you can determine whether how much time your program is gonna take to run. Like your logic, your programming logic would like make your program slow or fast. So time complexity is a way to determine whether your program is running slow or fast. That's the most layman term definition ever. So it depends on the input of from the user. That is n. Let's say this is the input from the user, and your program would depend on that input, and it might get in the order of O of 1, order of n. It might be in a constant order. It might be something like this. So all this is the like it's the run time. It's the time it requires your program to run. This is can be to call as time complexity. Okay, it depends on the n, and it also depends on the program you have written. So how can you tell that your program is not up to the mark, or maybe not properly optimized? If your time complexity is like exceeding too much and is not something like maybe n to the power n, this would take exponential time. This would take exponential time, and if you have written something, program something like this, your program would take a lot of time to run, and the this is what you can evaluate with a knowledge of time complexity. So in simple terms, it can be determined by how many number of calculations your program is doing. Let's say your for loop is running from 0 to n, then and this is the only thing your program is doing, then you can say that O of n is your time complexity. So this is the basic idea. So is this clear? Ayush Kejriwal, is this clear? Okay. So let's now, can you say what is the time complexity of this linear search algorithm that we just did? In this linear search algorithm, the only loop we run was from 0 to n. So, what is the worst case that can be possible in this case? Maybe our target element was present in this first box itself. That might be possible. Or in the worst case, it might be possible that the target element is in the last box. So both cases are possible, or in somewhere in the middle. So the best case is this one, and the worst case is this one. So we're gonna consider the worst case. Like, we're not gonna take the best case here. We're gonna consider the worst case, the maximum time your program can take. So at in this worst case, your program would traverse through the entire array one by one, and it would take n comparisons. So at this program, the time complexity is O of n. Is this clear? Okay. 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 So you don't have any doubts? Can we proceed to the binary search? Let's proceed to the binary search. And this is the code of the linear search algorithm that we just did. Now let's go to the binary search. Okay. So binary search is a much faster way and a much optimized way of searching than linear search. But it has a huge criteria to begin with. The first and foremost criteria of binary search that it is only applicable on sorted arrays. Sorted arrays or sorted search space, like something like this. The whole search space needs to be sorted. It cannot be in random order. Binary search cannot be applied in random order, random arrays, or random things. It has to be sorted in order to be binary search to be applied on it. So this is the first and foremost criteria of binary search. Now let's see what is the main idea behind it. Now this is the same question. Find element 8 among this array. So let's see the approach here. In binary search, we select a mid element. We take an average and select a mid element from it. In this case, in the whole array, this is the middle element. So our mid is this. Now, the first question we ask is whether the mid element Hello. Okay, so whether the mid element is equal to target element or not. So in this case, 5 is not our target. So we have a choice to whether go to the this part, or we can go to the this part. We have a choice because this choice is evident because only the array is sorted. The simple analogy behind here is that if if my target element is greater than the array of mid, is it possible that it might be present in this side, in the left side of the mid? If my target element is greater than ARR of mid, is it possible that it is present in the left side of the array? What do you think? It can be possible because all the elements in this side of the mid is less than that of mid. See, you can see 1, 2, 3, 4. All of them are less than mid because this is a sorted array. If our target element is greater than the element which we want to find is greater than mid, then we need to go to the right side, which is in this side, the green side, this one, this one. So is this clear? This is the simple logic behind binary search. Then end is equal to mid plus 1. End is equal to mid plus 1. In this case, end is equal to not mid. End is not going to be equal to mid plus 1. Mid minus 1 is equal to mid minus 1. Because we are going to go to the right side. In this case, in the first case, we're going to go to the right side. So we're going to update the start index to mid plus 1 because 8 is present at the right side. Okay, Ritaja? Yes, yes. So after this, we can omit one of the sides. So we decided to omit this one because this whole side is useless to us right now. Is completely useless to us right now because we know our target element can be present in this side. So we proceed with this side. So let's write again. Now this is our search space right now. This is our new search space. So again, we try to find a mid. We again try to find a mid. And at this stage, 7 is our mid. So again, the question arises whether 7 is greater than our target or not. So is target, which side we need to go? Visually tell, visually see and tell. We're going to go to the blue side or the green side at this point. Yes, obviously in the green side because 8, that is our target element, is greater than that of 7. So at the left side of the 7, our element can be present that is greater than 7. So we obviously need to go to the right side. So we omit this again, and our new array becomes something like this. 8 and 9. And at this point, we come up with that The mid falls at 8. So now is target equal to mid, ARR of mid? Did we find the element? Obviously, we found the element. Which is that? This index. And how many iterations did it take? It took 1, 2, and 3. So which one is more efficient, do you think? Is it the linear search or the binary search? Yes. In most of 99% of the cases, binary search is much more efficient than linear search. So can we code it up right now? Can we? Okay, then let's write the code. But first, let's see the approach which we're going to take. We're going to take a start index. At first, this would be the start index, and this would be the end index. We're going to calculate the mid by this S plus E by 2. That is start plus end by 2. By this formula, we can calculate the mid index. And this would give us a mid index. And by this, we're going to keep on calculating and we're going to keep on updating the start or maybe the end. And this way, by this way, we're going to implement the binary search. So let's code right now. Okay, let's copy and paste the first part because this whole part would be same. This is the user input part. And from here, we're gonna start the binary search algo. So this is just maybe let's take low and high. This is the starting index and high is equal to n minus 1. This is the ending index. So while low less than equal to high, now inside this while loop, we're going to calculate the mid because with each iteration, the mid will be updating. So we're going to calculate the mid with each iteration. So this low plus high by 2. And now we're going to start comparing. The first and foremost comparison is that whether a target if ARR of mid is equal to target or not. If we find that this is the case, then answer is equal to mid. Answer is equal to mid, and we can break the loop. Else if ARR of target element, maybe target element is greater than ARR of mid. This is which case when we need to go to the right side of the mid because target is greater than our middle element. So we can go to the left side. Obviously, we have to go to the right side. So we're gonna update the starting variable. We're gonna update the starting variable, that is low is equal to mid plus 1. Else we're gonna update the ending variable, that is high is equal to mid minus 1. Now let's show the output. If answer is equal to minus 1, cout element not present, else cout and present at index. So here is the code. Now let's run it, and after that we're gonna dry run it once and see what is the case going on. Wait a second. Something appears to be broken. Just a minute. Okay, so I think this might be working right now. Enter the size. We have entered. Let's enter the array elements. Because we are implementing binary search, the array needs to be sorted. This array that we entered has to be sorted. Otherwise, the binary search will not work. It simply wouldn't work. Now, let's try the element which we want to search. Let's enter 5. So element is present at index 4. Maybe now you can see element is present at index 4. So yes, our program is working correctly. And let's now run it again. And this time, let's enter something that is not present in the array. Let's say for 7. So element is not present in the array. So our program is running correctly. And this is the binary search algorithm. So is this clear? Is this approach clear, or any doubts? Okay. Yeah. So the thing that needs to be keep in mind, maybe the starting index, that the low at first is here and the high is at here and the mid is calculated to be here. Okay. If we want to go to this part, the right side of the mid, then we need to update low to mid plus one, that is this index. So at the next iteration, low becomes this and high stays the same. So we're going to search this part. This is how the algorithm, the program is working. And if we need to go to this part, the left part, somehow, then we're going to update the high, that is the ending index, to high is equal to mid minus 1. So the high becomes this one, this becomes the high at the next iteration, and the low stays the same. So by this, in with each iteration, we're going to take a decision whether to go to the left or to right. And by this, we're going to tell the program in which direction to flow. So this is the concept of binary search. Okay, so is this clear? Yeah. Now, what is binary search? You can go through this. Binary search is an efficient algorithm for finding a target value within a sorted array. This is the bookish definition. And now comes the time complexity. The time complexity of binary search is order of log n. And why is that? Let's see. When the arrays of size 8, when the arrays of size 8, with each iteration, maybe we can eliminate half of it. We can eliminate half of the array by deciding whether the target value is greater than mid or less than mid. So we can obviously omit the half of the array with each iteration. So at first the array size is 8. In the next iteration, the array size becomes maybe 4. And we again omit half of it, maybe this one on this side. So again, it becomes half of it. So now it becomes 2. And finally, it becomes 1. So is it close to log base 2 of 8? That is, it comes to 3 iterations. And at max, in binary search algorithm, it can go to log base 2 of n plus 1. So you can say this as log base 2 of n. This is the time complexity of binary search. The difference between linear search and binary search becomes more evident when the array is bigger, like much bigger, in a size of maybe 1,000 size array. In linear search, you have to traverse through the entire array. Maybe at worst case, you have to traverse the entire array. But in binary search, you can achieve that by in less than 10 iterations. So the efficiency of binary search becomes evident in large data sets. and not in small ones. Okay, so this is the code of the binary search. And let's compare between linear search and binary search in a quick way. In linear search, the obvious advantage in linear search is that the array needs no need to be sorted. It can be in random order, it can be in sorted, but there is no necessity to be in sorted. Binary search, there is a necessity that the array must be in sorted way. So this is the very first necessity that comes to our mind. Next, it is also called sequential search and it is also called half interval search. Sequential search in linear search, why? Because we go in sequence one by one and search for the element we are looking. And in binary search, half interval search because every time the whole search interval is getting halved. Because maybe in the first iteration the interval was the whole size of the array was 8. But as soon as the second iteration comes, it becomes 4. Or maybe would have already found the element at that point, but at max it can become 4. Then it becomes 2, and finally it becomes 1, and the result comes. So, and the time complexity of the linear search is O of n, and the time complexity of binary search is O of log n. So this is the difference and comparison between linear search and binary search. Is this clear? Yeah, okay. Okay. So let's proceed. This is the visualized way of comparing linear search and binary search. Like this is the way the searching algorithms operate. Linear search obviously goes one by one, as you can see in the diagram in the above. This is the way linear search is trying to find our target. Okay. And it goes on like this. Whereas binary search goes to the first mid, then again goes to the new mid, again goes to the new mid, and this way it finds the desired element. So how many jumps can you notice here? There's 1 jump, 2 jump, 3 jump, 4 jump, 5, 6, 7, 8, 8. And while in binary, 1, 2, 3, and 4. So this is the advantage of binary search. Now, those who are present here, have you solved any Leetcode problems? Any Leetcode problems? A single, any one? Have you solved any? Okay. Yep. Any other? Okay. So two answers. See, the most fun way to improve in DSA is practicing Leetcode, to be honest, because by that way you can like truly start improving in DSA. And Leetcode is a fun way to practice, to be honest. So yeah, and this question is from a Leetcode. This is a Leetcode question, but we're gonna solve this in maybe in local peak index in a mountain array. So this is our next binary search question. the first question comes to our mind: what is mountain array? What do you think from the name? What is mountain array? A mountain appears like this. Like at first, it is an incline and then it declines. So same is the graph of this array. At first, it inclines and then it starts declining. So this is the kind of array we are calling mountain array. You can see the first element is 1, 3, 5, 6, and at this point, it was increasing up to till this point, and this is the peak. This is the absolute peak at which this is the maximum value of the array. And after this, it steadily declines. If our element is something like this, like something 8 appears here, then this can be called a mountain array. This is something else because the steady decline was interrupted. The steady decline was interrupted by a larger element here. So this is not, that was not valid mountain array. So is the definition of mountain array clear? Then we're going to solve the problem of finding the peak index in the mountain array. Yeah. Okay, so the peak index in the mountain array. Now there might be 3 cases when we try to apply binary search in this kind of program, because this array is not completely sorted. You can see this is not completely sorted. There is a gradual trend of uprising and then a gradual trend of decreasing. So our mid can fall in maybe this area where the values are increasing, this part, this whole part where our values are increasing. Our mid can fall in this area, or maybe our mid can fall at the peak, or maybe in the declined area. So if we find our mid to be falling in this, what's the next step we're going to take? Are we going to go to the right or the left? Because we need to find the peak. The question tells us to find the peak. So if we find ourselves at this position, do we need to go to the left or right? Try to answer in the chat box. Okay, so if we find ourselves at this point, we would try to go to the right side, because the mountain array is such that if we are at the slant, increasing slant, then we would try to go uphill, because the peak would be present at the right side. If we go to this side, the peak can be present at this side because it is steadily decreasing at this side. So it would only make sense if we go to the right, and vice versa at this point. If we find ourselves at this point, the mid falls at this point, then there is no point of going to the right. The only logical solution is going to the left, because at left the array is increasing. The array values are increasing. So the clear-cut answer is that where the array values are increasing, we need to go to that direction, because by that way, we're going to find the peak element. And this logic we're going to use to write the binary search. Is this simple logic clear? That when we need to go to the left, or when we need to go to the right? Ayush, Ritoja. Okay. Okay, if the logic is clear, then we can write the code for this program. So int n, ns, all that. So at first, we're gonna take the size of the array from the user, enter the array size, and let's store it in. Now let's take the array elements. Enter the array elements from and we're gonna run the loop from I is equal to 0 and to I is equal to n minus 1. That is n I is equal to I less than equal to n. We didn't declare the array. Okay, so the input part is ready, and now we are searching the mountain peak, searching the peak element. Let's take S for starting. As the starting index, we're taking S, and as the ending index, we're taking E. That is equal to n minus 1. Why S is less than equal to E? Let's calculate the mid. S plus E by 2. And the first thing we're going to compare is that whether the element is at peak or not. How can we say that the element is at peak? If both the element at left and right side is less than the element at present. What I mean to say is that in this peak, in this element, in the sixth element, which is at index 0, 1, 2, 3, you can find that the value is 6. Both the left and right, that is 5 and 4, is less than that of 6. This is the only condition required for us to determine whether that is a peak or not. So we're gonna use this logic to search whether this is a peak or not. So if error of mid minus 1 is less than error of mid, and then error of mid plus 1 is less than error of mid. else if ARR of mid is greater than that of mid minus 1. This implies that we are in increasing stage because the mid minus 1 is less than that of mid. Then we can easily say that it is in increasing state. So we need to go further uphill. So that's why we're going to go to the right. So let's update the starting value. X is equal to mid plus 1. Else, we're going to update the ending value. E is equal to mid minus 1. Now let's print peak index. Let's check whether everything is correct or not. The search space doesn't need to be from 0 to n minus 1. It can be from 1 to n minus 2. Because obviously the first and the last element can't be the peak element. Because it is starting from here. The array must be of 3 size at least. So the first and the last element can be the peak because those are the boundary elements. So we have to search between this starting from 3 to 4. So we can apply this logic here and update the search space like this. The starting index is from 1 and the ending index is up to n minus 2. That is the second last index of the array. So now let's check that is okay or not. Enter the array size, enter 6, and let's enter the same array 135642. 135642. So 0, 1, 2, 3. The peak index is 3. You can see this is the first 0th index. This is the first index. This is the second index number 2, and this is the index number 3. 6 is obviously the maximum. That is the peak of the mountain array. So our program is giving the correct answer. So is this logic clear? Ayush, everyone. Okay. Okay. Any doubts? Any doubts regarding this program? Because this is a kind of tricky one. Okay. So no doubts. Now, if you guys are accustomed to it, Leetcode, can we just go to the Leetcode problem section and solve that mountain array problem here right now? Say yes if you want that. Okay. So this is the peak index in a mountain array, the Leetcode problem. We're just gonna copy paste it because we have already solved the problem. The searching part is only the part we need. The input is already provided in Leetcode problems. And it's same ARR. We we don't have to print. We have to return the answer index as an answer. And let's see. So we need to declare answer as well. Okay, the n is not declared. Okay. Let's declare the n first. Int n is equal to ARR of size of ARR, and this. Okay, accepted. So let's proceed and submit. Okay, you guys know about the Leetcode system, right? How this accepted thing works, what are test cases. Okay. Okay, so yeah, it's accepted. So you can probably solve it later on by yourself. Try to solve it by yourself. We'll be providing the code as well. So let's now solve another problem of binary search, that is find first and last position of element in sorted array. Now I want you guys to come up with some kind of approach for this problem, because the first thing to note down here is that the array which were given as an input might contain duplicate elements like this one. There are 2 7s, there are 2 8s. So in this case, the target is given 8, and we have to return the first index at which 8 is appearing in the array and the last index at which 8 is appearing. So this is not the usual binary search. We just need a little bit of modifying the algorithm, and that would work. Yes, you can answer.
First, we can check from the front when the element appears the first time, and after that, we can check from the end, like starting from the end element, the first time that it is appearing, that will be the last index position.
Yes, but this is the approach you told. It's of linear search.
Yeah.
If
Oh, okay.
we
Binary. So,
we need to find in binary search, because see, this is the time complexity thing we are talking about. You must write an algorithm with O of log n runtime complexity. So linear search won't work here. But your approach was right in case of linear search. So let's visualize this problem. We're gonna first copy that array. Just wait a second. 5 7 7 8 8 10. The target is 8. 5 7 7 8 8 10. 5 7 7 8 8 10. The target is 8. We need to find the first index at which 8 is appearing and the last index at which 8 is appearing. So if we do a linear search and start searching from here, as I was told, we can easily get the first index by this. And if we start searching from right, From the last, we would get the last index. But how to do it in a binary way? We can do one thing. Because the array is still sorted, we can obviously, the first criteria meets of binary searching, that the array is still sorted. We can apply binary search here as well. So let's see. Let's do a dry run here. The first mid would be appearing right here. That is 0. Let's write the index 0, 1, 2, 3, 4, and 5. The first index, the first mid would be appearing at this. Let's change the color. This would be the first mid. Okay. So obviously, is 7 greater than or less than 8? 7 is less than 8. Our target element is greater than that of 7. Then we can omit this part. We have no use of this part. Am I right? So we can proceed with the blue part here. So the new search space become like this. We updated the first index, that is this, and this is our new search space. The index is 3, 4, and 5. Okay. Now a new mid will be calculated, and this time this one is the mid. This one is the mid. So now we stored this index somewhere. Maybe we stored this index, and so this is the fourth index. We stored this somewhere. And when we are trying to find the first occurrence of that element 8, we would have to like go to the left side. Is this logic clear? Like, for the first index to be found, we need to go to the left side. The first index, the left side element might be 8. We can't tell at this point, but it might be 8. So we have to tell the binary search to go to the left side. But if we want to find the last index, we have to go to the right side. Is this clear? While storing the answer as well. So, for example, let's take, we want to search the first index at this case. We would store the answer 4 somewhere because we have found the element 8 at an index 4. But still, we want to find whether element 8 was present before as well. So we updated it again. And this time, the only search is 8 because we omitted this part. We omitted this whole part. And this time, the only search space is 8, that is index 3. And mid falls in this index as well. And we again find that at this index, mid 8 is also present here. So we updated answer from 4 to 3 because now this is the first element at which 8 was appearing. Is this clear? Okay. So let's write the program. Find first and last position of element in sorted array. Now I would do it in a modular fashion. In index 1, first occurrence of nums target, we are passing it in a function. Index 2, first, this would be the last occurrence. nums target, and we just need to return it later on. But for let's write the function first. The function would have a return type of int because we are gonna return the index. So let's write the first occurrence. Vector in nums and target. Okay. Okay. And s is equal to 0 is equal to nums dot size minus 1. That is the last index. And while s is less than equal to e, we're gonna keep on the binary search. Let's calculate the mid. S plus e by 2. And at first we're gonna check whether the target is met or not. So if norms of mid is equal to target, then we're going to store the index at first because this is the possible answer. This might or might not be an answer, but we have to store this. Answer is equal to mid. Then we have to, since we are going to search for the first index, we have to go to the left side. So in order to go to the left side, we're going to update the end one. So this is the case. Else if norms mid target, if the target is greater than that of norms of mid, we need to go to the right side. At is equal to mid plus 1, else is equal to mid minus 1. And at last, we return the answer index. Let's declare the answer index first. We haven't declared it yet. So this is minus 1 declared. If at any point of time, like the program might give us such a problem that the target element is not at all present, then since the answer, this criteria would never be satisfied, nums mid is equal to target would never be satisfied, the answer would never be updated to mid, and it will always stay to minus 1. So if at last we see that our answer is coming minus 1, we can say that, okay, the element was not present. So this is the logic. We're gonna quickly copy paste and write the last occurrence function like this as well. The only change we're gonna make is this, because we're gonna trying to take the last index. We are trying to go to the right part. So instead of this e is equal to mid minus 1, we're writing this s is equal to mid plus 1, and everything else can stay the same, and we are returning index 1 and index 2 is the answer. Now let's check. There might be some problems. Okay, accepted. So let's go ahead and submit. Okay, so yeah, this is working fine. And is this clear? Ayush, Shomo. Okay, let's something. Why not just find the first index from left and then subtract from the length, it will give index from last. Length of what? Length of the whole array. But then how we'll be getting the last index at that point? Let's see. Okay, you're telling that maybe we find the first index, that is in this case, is this visible? Look at this area. We are trying to find the first index, that is 8. In this case, it's 0, 1, 2, 3 at position 3. And we are trying to subtract it from the length of the whole array, that is 6. 6 minus 3 is again 3. So that would not give us the right answer. The only way to find out whether how many 8 are present is to search again. Like you can go through a linear searching way, or maybe again, there are many approaches, but you can't subtract like this and get the answer. Am I getting you right, Ashish? Yeah. So did you understand the logic behind this? Give a thumbs up. Can you explain the whole program in short? Yeah, sure. Okay. So we have divided the program in two parts. This is the most easiest way. At this part, the first occurrence function, you can see this is the name of the function, first occurrence. We are searching for the first occurrence of the target element. And in this case, we're searching for the last occurrence. So for searching the first occurrence, at first we need to find whether the target element exists or not. This is the same binary searching algorithm that we are trying to learn. But the only difference here is that instead of just ending the program here and become for sure that this is our answer, we are storing answer, the mid value in an answer variable, and we are trying to go for the left side because see, let's visualize. Maybe this is a long array, something this was present here, and there are many 8s present in an hypothetical array, and our target is 8. Okay, and there are many elements in right side as well. Somehow our mid falls in this, somehow our mid falls at this index. Okay, so we found out that yes, 8 exists in this array and it is at index number this. Maybe let's say this index number 10, 9, 8, 7, 11, 12, 7, 8, 9, 10, 11, 12. Okay. So this is where the mid falls. Now, we don't know whether there is an 8 before this 10 index, but we found the 8 at here. So we are going to immediately store that. Maybe we can find in the this side as well, but we're going to store first. So we're going to store the index and then we're going to try to go to the left side. So that's why we're updating the end value, the high value, the end with mid -1. so that this site searching can occur. So obviously this would be found eventually only if we start searching this site. If we start searching this site, the last occurrence will be found. If we start searching this site, the first occurrence will be found. Is this logic clear? Okay. So this is the whole program. This is the only tricky part of this whole program. The whole last occurrence and first occurrence function is exactly the same, just this line is different. Because we are trying to find the first occurrence here, we are trying to shift to the left. That's why we are updating the end index to mid -1. We are decreasing the end index. And because here we are trying to find the last occurrence, and that's why we're updating the starting index. We're trying to shift to the right side. This is the only difference. And now we stored both the indexes in index 1 and index 2, and we returned it in form of an array. This is a vector. Okay. Vector is nothing but a dynamic array. You can uh, go look it up. Vector is nothing. The whole thing operates like an array. Just it has more functions built in, and it operates. It can change its size in runtime. So we returned it as a array, as the program stated us to do. So is this now clear? Okay. Okay. So any questions? Any questions? Any doubts? You can ask. Okay. Who are those who told that they are doing lead code? Like they are solved lead code? Raise your hands once. Okay, Ayush only. Okay, okay. Good to see. Avinash. Okay. Okay. Okay, cool. Keep going. And if you want to solidify your DSA knowledge, you have to do lead code. So I advise every one of you to solve lead code problems. This is the best fun way to learn DSA. And yeah, with that, maybe we can end our session. Okay. Avinash, you want to ask something? Okay, okay. So follow the socials, and this is the GFZ social as well. Okay, okay. Great. So yeah. Okay, now the session is coming to an end and you can leave the meeting. Thank you all and keep practicing.